In this lecture, we shall have a general discussion on signal detection theory. Signal detection theory is used to model the process of decision making with uncertainty. This is commonly used in communication, especially in radar communication. It is also used in medicinal fields of psychology. The performance of any receiver is basically a function of two properties of the receiver or the observer. Those two properties or parameters are its sensitivity and its decision criterion. Sensitivity denotes the ability to tell two signals apart, and criterion denotes how the receiver or the observer chooses to respond to the signal. So to assess these two parameters independently, we need the signal detection theory. The signal detection theory was first introduced by radar researchers around the Second World War time. It is actually used to discriminate the radar signal and the noise. The aim is to maximize the correct detection and minimize false alarm. For example, the radar operator or the receiver will be getting a display like this, which shows the targets or some obstacles that are coming in or moving in the area, but it's not visible whether it is a fighter jet coming in the direction or it may be some flock of birds. So if you correctly tell that it is a fighter jet, it is a correct detection. But if you misunderstand this flock of birds as a fighter jet, then that is a false detection. So our aim is to maximize correct detection and minimize the false detection response. As we know, any receiver which receives a signal from outside will get the signal and some noise. This noise may be an external noise or an internal noise that is generated from the device itself. However, at the decision making point, the received signal or the stimulus will be consisting of the signal and a noise. So the receiver or the operator or the detector has to tell whether it is a signal or a noise. It has to decide whether it is a signal or a noise. So how to make this decision? How to change the parameters or how to make a proper decision? That is what we discuss in the theory of signal detection. As we discussed, the signals are always accompanied with background noise. This background noise can be background luminance or a background noise that is always present there, and we should not detect it as a signal. And then there can be distractors or false signals or some unrelated signals that are coming inside. So we should not detect them also as targets. So two kinds of noises may occur. So anyhow, for any sensory input, the brain or the detector or the receiver has to interpret its meaning and decide whether it is a signal or noise. So this decision making, to make it simple, we will do the decision making according to some criterion. We will set a criterion and we will force the choice, which means if the signal is above a certain criterion, we will say that it is a yes, it is a signal. And if the signal level is below that criterion, we will say it is a no and it is a noise. So we will decide whether it is above or below that threshold level. This criterion is also called a threshold in communication. So we will set a criterion parameter and we will decide whether it is a signal or a noise. This is the confusion matrix involved in such a detection. You know that this is a binary detection. We are deciding whether it is a signal or a noise. That is a binary decision. So in such a decision, these are the parameters. I will explain what this is. This is the stimuli or the incoming signal. The incoming signal can be a signal or a noise, and our response to that, this is the decision. Our response to that is either a yes or a no. What it means is there can be 4 outcomes in this experiment. At a time when the signal is coming as input and we say yes, that is a correct hit. The signal was the input and we said yes, it is a signal, so that is a correct hit. On some other time, the input was noise only, but we detected it as a signal and we said yes, that is a signal, but it was actually a noise, so that is called a false alarm. There was no signal, it was just the noise only, but we said yes, so that is a false alarm. In the next case, a signal was coming but the power was less and we thought that it was not a signal, it was a noise, so we said no. So we actually missed a original signal, that is a miss. And then the fourth condition is the input signal was a noise, there was no input signal, and we said no to that, so that is a correct rejection. So there can be 4 conditions in this: a hit, a false alarm, a miss, and a correct rejection. These are the 4 outcomes of a binary detection process. Signal and noise. The noise can be an external noise that interferes with the signal, probably in the channel, and there can be internal noise also that is generated inside the receiver itself, so that may corrupt the signal representation. So somehow the representation will be, if we represent the representation as RS, it will be a sum of the signal and the noise. So how can we decode the original signal S from this RS, and how to avoid the noise? If the noise is a white noise, then the received signal plus noise will usually follow a normal distribution. As you can see here, the x-axis is the signal power, or whatever parameter of the signal that we are measuring, and y-axis will be the probability. So let's consider this as an amplitude. So the average amplitude of the signal will be at this point, and at some time the signal may have a higher amplitude or higher magnitude, and there can be signal samples at lower amplitudes also, but the average value will be this one. So at the average value, the probability will be maximum. That is what this means, and this shape is what we call it as a normal distribution. So in a white noise environment, the noise will be getting added to all levels equally. That is a white noise. So in a white noise environment, the signal will follow a normal distribution. Now coming to the distribution of noise, if it is an additive white Gaussian noise, the Gaussian distribution also is following a normal distribution shape. So here you can see that both the signal and the noise are having same normal distribution. Here this is the mean noise or the average noise power, and at that power you have the highest probability of finding the noise. Then this mu s and mu n are the mean of, this is the mean of signal, this is the mean of noise, mean, or in other terms it is average. So this is the average signal and this is the average noise. So as we know, the signal power will be usually greater than noise power, so mu s is greater than mu n. So if you plot both the signal and noise in a same graph, the signal will come right to the noise. That means the green graph will come here. We'll see how this comes. So if mu s is higher than mu n, that is, this is mu n, the mean of this noise, and this is mu s, mean of this signal. So since this is an x-axis and this starts at 0, this is increasing in the right direction. So the signal will come right to the noise, and from this will be our received input. It will be consisting of both signal power and noise power. Noise power and signal power. So from such a signal plus noise, we have to decide whether it is a signal or noise. So it depends upon how we make the decision. Sometimes the decision is hard. That is, if these two are a bit distant, that is, if noise is at a level and if signal is at a different level, we can easily determine which is a noise and which is a signal. But if the amplitude or the magnitudes of their powers are almost equal, that means if they overlap like this, it is hard to detect whether it is a noise or whether it is a signal. From this type of distribution, it's really difficult to understand whether it is a signal or a noise. So what to do in such conditions? How we will set the criterion for decision? That is what we are going to do. So if we have a distribution like this, that is, the noise and the signal are overlapping, we will choose a criterion. This blue line is the criterion, or in other words we can call this as a threshold value. So this is a criterion or a threshold. So comparing the signal with the criterion, we can decide, or we can force decide whether it is a signal or a noise. So we have selected a criterion level, criterion amplitude level, and we will decide that we have decided that whatever comes right to this, that means whatever value signal power comes above this threshold value, we will consider it as a signal. That is, whatever signal input signal level that comes above the criterion level, we will call it as a signal, and whatever value of the signal that is coming is less than the criterion, we will call it as noise and we will discard it. So we have set a criterion. This is the threshold level, and right to that is the signal and left to that is noise. So in setting such a criterion, there may some problems that arise. There will be some problems that arise in setting such criterions. This is a hard decision point. So what are those problems that are occurring? We'll see. So in this, if we have to take a decision at this area, we can easily say that this is a noise. If we have to take a decision at this area, we can easily say this is a signal. But when it comes to areas closer to the criterion, it is hard to determine whether it is a noise or a signal, because it can be, because these two graphs, or this noise and this signal, are overlapping. As you can see, in this area there is some portion of signal also. So if we choose this portion as noise, that is, if we choose the whole portion left to the criterion as noise, we are actually discarding some portion of signal also. So this could be potentially a signal, and to the right of this criterion we are calling everything as a signal, but in that some noise is occurring. So this could be actually potential noise but we will call it as a signal which may produce which may be a false alarm. So these two issues may occur in setting such a hard decision. So you will again see how it occurs. In the first graph, we are considering the signal alone, and we have set the criterion, and whatever right to the criterion is signal, and we will miss this much portion of the signal. So this much portion we will call it as noise, but actually it is a signal. So it will come under the name miss. So we are missing this part of the signal. So this is mentioned in probabilities. So this is the area under this curve is the probability of correct hit, and the area under this portion is the probability of miss. Here we are considering the noise. So whatever left to the criterion is what we call the noise. So this is the probability of noise, the area under this curve up to this, and the area under that same curve in the right side of the criterion is the false alarm. So this is easily understood. So it is represented in a table also. Here this whole green graph is the signal, and the area under the green graph is the probability of signal detection. So in that signal detection, a correct hit will come and some misses will come. So this misses plus this hit will form the 100% of the total area of the signal. In the noise, this is a correct rejection and this is a false alarm. By adding false alarm and correct rejection, you will get the total area of the noise or the total probability of noise. So that is a 100% here. So as we have discussed, the probability of hit plus probability of miss is 1 or 100%, and the probability of false alarm plus probability of correct rejection is 1 or 100%. So if we know one parameter, we can calculate the other. In this also, if we know one parameter, we can calculate the other one. The overall decision difficulty is determined by the signal noise relationship. The relationship between the signal and noise is defined by a term sensitivity. It is actually the distance between the peaks of the noise and signal. The actual performance will depend on the decision criterion, where this decision criterion we are setting it on, but the decision difficulty will depend on the sensitivity. The sensitivity parameter, if it is less, that means these two graphs will be overlapping at more area, so it will be difficult to determine whether it is signal or noise. But if the sensitivity is high, that means these two peaks are at maximum distances apart. That means there will be very less overlap only, so it will be easy for detection. So the difficulty of detection is determined by the sensitivity parameter. This sensitivity parameter is also called discriminability, and it is denoted by D prime, D apostrophe. So it is a measure of how close the signal and noise are, how much overlap is there, and it is supposed to be a property of the sensory process. The other parameter that we already studied is the decision criterion, the response bias or the decision criterion. It is where we take the decision, measure of what is considered as noise and what is considered as signal. It is susceptible to motivation, strategy, etc. It depends upon the receiver. So according to the type of system, we can set the decision criterion at a certain level. If we don't want to miss any signal, we can move the decision criterion to the left. If you If we want to select the only the proper hits only, then we can move the decision criterion to the right side. So like that we can set the decision criterion or the response bias. This sensitivity and the criterion are two independent parameters. They doesn't have any relation in between them. So here is a graph showing all this. Here first we will see about the sensitivity. So as I said, sensitivity is the distance between these two peaks, or how much apart these signal and noise are. Here you can see it is close compared to this one. So this is low sensitivity, this is high sensitivity, because this is more apart than this one, right? Okay, then coming to criterion. This criterion is set on the middle of these two graphs, or at the intersection point of the noise and the signal. So this is called a unbiased criterion. We doesn't have any biasing. Half of the total signal power is selected as the criterion point, and whatever comes right to this we will call it as a signal, and whatever comes left to this we will call it a noise. Now if we are placing this criterion at some other point, we will call it a biased criterion. That means if we are moving this criterion point to the left, then it is a biased criterion. That means at this point we will not miss any signal. All the signal probability comes in the signal decision hit. So this is a biased criterion. We have moved the criterion point from the intersection or the neutral point. This is the same comes in the case of sensitivity also. Now, as we said, the y-axis is the probability of occurrence, and x-axis, what is the parameter on the x-axis. This x-axis can be any real measure, whatever parameter we are measuring. If we are measuring some amplitude or magnitude of a signal, it can be a voltage. If we are measuring frequency, this can be in hertz. If we are measuring length of some signal or something, then it can be unit of distance. So according to whatever parameter we are measuring, it will come on the x-axis, and we can convert this whole graph into a standard or normalized one by using the deviance scores. Here this is the current value, this is the average value, and this will be the standard deviation. So by doing this we can normalize the real values to a standard value or standard graph. Now computing the sensitivity, or the other name is discriminability index. It is denoted by the term d prime. This is called as d prime, and it is given as the separation divided by spread. This is the separation between the two peaks, and the spread is the standard deviation of the signals from its mean value. So as you can see, this is mu s and this is mu n, and the distance between them is calculated by mu s minus mu n, and it is scaled by standard deviation of the spread. So in this case, both the noise and the signal are having same normal distribution, so we can set this we can calculate this d prime using this equation. But if the noise and signal are having two different types of distribution or two different spreads, then we have to use a complex equation for calculating the d prime. So it depends upon the spread of the noise or the signal. Now setting the decision criterion. As we said, if we are setting the decision criterion at the intersection point of the noise and the signal, we call it as a neutral criterion. It comes in the center. Whatever comes right to it is a signal, whatever comes left to it is a noise. But here we can change the position of the criterion. That is, here 3 positions are shown. This is the first position, second and third. At the first position, this is the first one, we call it as a liberal criterion. So the selection is liberal. That means whatever signal that comes in the range of signal detection signal, we will call it as a signal. That means in that case we will not miss any signal. The probability of hit is 100. That means we will not miss any original signal because the criterion is at this point. So whenever a signal comes, we will call it a signal. But at that time a lot of noise also is coming beyond that level, so the probability of false alarm also is very high. Probability of false alarm is 0.84, probability of hit is 1. Probability of false alarm 0.84 means this noise curve is having this much area right to the decision point. That is why it is 0.84. This D prime is same for all graphs. That is why D prime is 2 for all the 3 conditions. So this left point we call it as a liberal criterion. The selection of or the decision of the signal is said to be liberal. At the central point or at the intersection of the noise and the signal, it is a neutral criterion. And in the third position, we call it a conservative decision criterion. What it means is we are not willing to take any noise as signal. So we will call it a signal only if we are 100% sure that it is a signal. So the probability of hit is very less, 0.16, because the area of the signal graph right to the decision point is very less only, 0.16 only, and but in that area there is no noise coming in. The noise is ending here. No noise is coming in the portion right to the conservative decision point, so that the probability of false alarm will be 0. So according to our application, we can set the threshold value or the criterion. So in some cases we will not want to miss any signal, so we will set a liberal criterion. In some cases we will just choose it as a neutral criterion, and in some cases we don't want any false alarm, so in that case we will set a conservative criterion. So those are the 3 types of criterions that we can choose. So these values, these positions we can vary according to our application. These all are threshold levels. This we can select according to the application. Now there is one relation between false alarm rate and hit rate. It is called receiver operating characteristics, or ROC. It is also known as ROC curve. So it is the relation between hit rate and false alarm rate. Here the x-axis shows the false alarm rate, y-axis shows the hit rate. So we can see here this is a liberal decision point or liberal criterion. So when the criterion is liberal, the probability of hit will be higher. So the probability of hit will be almost near 100 here, the green one. Here it is not that much liberal, but it is not too much conservative also, so it will come here. Here the red one, it is somewhat conservative, so the probability of hit will be less. That is why the hit rate is around 50 only here. So it depends on the criterion point where this point comes in, and this shape of this graph or this blue line comes according to the sensitivity of the receiver, that is the D prime. So this line is corresponding to one value of D prime, and on that sensitivity you can have different decision criterions. You can see that in all these three graphs the sensitivity or the D prime is same. On that same D prime you can have three decision points. So it is the relation between probability of hit and probability of false alarm. We will see a better example for this one. Here these two are having a large overlap. That is, this is the noise, this is the signal. It is having a big area of overlap, and the D prime is less. D prime value is 1. So that graph will come here. If they are somewhat apart, the overlap will be less. The D prime value will be 3. That means the distance between the two peaks is larger than this one. So at that time the probability of hit is higher and probability of false alarm is less. So like that, for each sensitivity you will have a curve here, and on each curve you can have different decision or criterion points. So that is about ROC curves and different sensitivities. To summarize, the underlying model of the signal detection theory consists of two normal distributions, one to represent the signal and one to represent the noise. The willingness of the person to say the signal is present in response to an ambiguous stimulus is represented by the criterion, and the ability of the person to discriminate between the signal and the noise is represented by the term sensitivity or D prime.